Hey guys, I am Gautam and welcome to EasyChemics. So in this video, I am going to talk about these topics, that is spectral line of hydrogen-like systems, and I will also discuss the Sommerfeld atomic model. So in the last two videos, I have already discussed about the fundamental particles, the old quantum theory that includes the Bohr atomic theory, and I have told you that Bohr atomic theory has a lot of contradictions. So to solve those problems, those are present in the Bohr theory. That means Bohr theory was trying to develop the exact atomic model, how the electrons, protons, and neutrons are present in an atom, or how the mechanics works over there. Okay, so Bohr tried to solve those problems, but he was not totally succeeded. Okay, so to solve those problems, then Sommerfeld came and solved a lot more problem. Okay, and finally we will discuss that problem. But uh, if you don't want to understand all those topics very clearly, just I would recommend you to watch those videos, those two videos first. Okay, so you will get two videos in these I button. Okay, so click on the I button and first check out all those videos. So whatever, let's start these videos. So now what I will discuss in spectral line in hydrogen like systems. I actually already explained the Rydberg equation. Okay, that is generally the spectral line properties. Okay, that explains the spectral line properties. And in this video, I won't discuss the Rydberg formula because I have already discussed that one in my Bohr theory, Bohr concept. Okay, Bohr theory concept, Bohr theory videos. So in this video, I will solve a lot of numericals based on Rydberg equation. So those are very important. Actually, these problems are important in your JE main, JE advanced examinations, and also this is important in your masters, and also this will be important for your IIT JAM, NET, and GATE examinations. So this topic is very advanced because this is the base of quantum mechanics. So if you want to understand quantum mechanics, so these things need to be cleared. Okay, so let's start. So let's solve a lot of problem. But before this, what I will discuss, let's have a look at that. So this is a shortcut. Okay, so LBP BPH. So this is the way how I remember the spectral lines. Okay, and how those things are related to spectral lines. So this is the shortcut. Okay, so I will teach you that how to remember the spectral line properties and how to remember the spectral series. So L means Lyman, B for Balmer, P for Passon, B for Brackett, P for Pond, H for Humphreys. So LBP BPH. So this is the shortcut of the corresponding spectral lines or spectral series names. Okay, so that I invented, or I discovered that one so that I can remember all those properties consecutively. So now then I will solve a lot of numericals based on Rydberg equation, different kind of numericals, all possible numericals. Those are important for IIT JAM examination. And finally, I will discuss the Sommerfeld atomic model that explains the fine spectrum. Actually, if you have seen my last two videos in the Bohr theory, especially the Bohr theory video, then of course you will find that Bohr theory couldn't explain the fine spectrum present, okay, in atomic system, or fine spectrum present in the corresponding spectra. Okay, so Bohr theory failed to explain the fine spectrum, but Sommerfeld model will explain that one, and that contradiction will be plus point for both for Sommerfeld model. Okay, so Sommerfeld started his works from there, that Bohr could not explain the fine spectrum, so he thought that he should start to solve that problem, and finally he did. Then I will discuss the how penetrating power or scanning power came. Okay, so you know these terms. Okay, in your graduation you have read already in your first year, but you don't know how these terms, these nomenclatures came. Okay, or how these generally works. Then I will discuss some merits and demerits of of Sommerfeld's model, Sommerfeld's atomic model. So Sommerfeld's atomic model will not be exact atomic model, okay, because it has also some classical mechanical concepts, and some quantum mechanical concepts. So both classical and quantum mechanical. So it is also a part of old quantum theory. So I will also discuss some merits and some demerits of Sommerfeld atomic model. Okay, so this will be our discussion of today's videos. So let's have a look at different spectral lines. So you know that this is the nucleus and this is the first orbit. Okay, that is n equals to 1, the second n equals to 2, 3, 4, 5, 6, and n equals to 1 orbit is also called K, L, M, N, O, P. Okay, so and so on. So you know already this one from your class 10, class 9 level things. But now what is important, that in this section, if transition occurs to, remember this one, if transition occurs to n equals to 1, that means first orbit, or from first orbit, okay, then I will get Lyman series if transition occurs from second, that means n equals to 2 orbit, or transition occurs from this one. Okay, so that means when from any other orbit electron comes to n equals to 1, I will get Lyman series. Even if electron goes from n equals to 1 to n equals to other series, so I can tell this in the opposite way. Okay, that will be absorption of energy. Okay, but in general, when electron comes to n equals to 1, that means first orbit, then I will tell that I will get Lyman series. Similarly, for n equals to 2, if electron jumps to n equals to 2, that means this level from any other level, then I will call that Balmer series. Similarly, n equals to 3 to this is called Paschen series, n equals to 4 this is called Pfund series, and n equals to 5 that is called bracket series. Okay, so and so on, and n equal to 6 that will be Humphreys series. So this is how it works, L, BP, BPH. So I have already told that. Okay, this is the shortcut. So, and energy increases when you go to if you increase the distance from the nucleus. So the energy of n equals to 1 will be lower than n equals to 2, and n equals to 3 will have much more energy than n equals to 2 or n equals to 1. So energy increases when the distance of the orbit increases from the nucleus. So this is how energy generally changes, okay, in an atomic system. This is completely I have got from Bohr theory. So this is the shortcut of Bohr theory. Okay, so now how we can solve a lot of problems, but before that we have to understand how alpha, beta, gamma, delta line works. Okay, so for Lyman series you will have alpha, beta, gamma, delta line. For Balmer series you will have alpha, beta, gamma, delta line. For Paschen series you will have alpha, beta, gamma, delta line, and similar for others series also. So how we will get alpha line for Lyman series? So for Lyman series, that means transition will occur to n equals to 1. So from any other higher energy orbit, if electron comes to n equals to 1 orbit, okay, so that will be Lyman series. Okay, that will be that we will call n equals to Lyman series. But if the difference of this transition is 1, that means if electron transits from n equals to 2, that means second orbit to first orbit, then that will be alpha Lyman series. If electron comes from n equals to 3 to n equals to 1, that means third orbit to first orbit, that will be beta Lyman series. Similarly for 4 to 1 gamma, 5 to 1 delta. Okay, so this is for Lyman series alpha, beta, gamma, delta. Similarly for Balmer series you will have alpha, beta, gamma, delta lines. That means if transition occurs from 3 to 2, then you will have alpha Balmer series, 4 to 2 beta, 5 to 2 gamma, 6 to 2 delta, and so on. Okay, you can explain other things also. I have already marked all those points, so just pause the video and understand what I have shown you. So these are called alpha, beta, gamma, delta lines. Okay, and I have told you that alpha, beta, gamma, delta, this is true for all series. So for Lyman series you will have all these lines, for Balmer series you will have all these lines, for Paschen series you will have all these lines, and so on, right? So I have discussed these equations, all these equations, whatever equation you are seeing over here. Okay, so I have discussed all these equations in my last video, Bohr theory video, and I have shown all the detailed calculations present in Bohr theory. So that video will help you a lot if you have seen that video. Okay, so the question is, let's solve a lot of questions. Those are important. So the first question is, let's calculate the radius of the first Bohr orbit, velocity, and the energy of the electrons of helium plus in the ground state in both CGS and SI units. So you have to calculate first Bohr orbit for helium plus system, velocity for helium plus system, velocity of electron of course, and energy of the electrons for helium plus systems. Remember, based on this Rydberg equation, that means the equation what we get from Bohr theory, that equation is applicable only for one electron system. So you cannot apply these equations in case of 2 electron systems or more. Okay, so those are true only for 1 electron systems. So helium is 2 electron system, but helium plus is 1 electron system. Similarly, lithium 2 plus is 1 electron system, beryllium 3 plus is 1 electron system. So these things are important. Okay, so remember, if the system is not 1 electron system, you can't apply these theories or these formulas, whatever I am applying over here, right? So in case of CGS system, let's calculate the fast Bohr orbit. That means Rn, and for fast Bohr orbit that will be Rn equals to 1. So I have put n equals to 1, okay, in the ground state of course. So if you put n equals to 1, you will get that, and if you put the value of Planck constant, the value of mass of electron, the charge of the system, okay, the number of proton in the system, and E, that is number of the charge of the electron. So as we are calculating in CGS unit, we will put all the values in CGS unit. So I have put all the values, and finally I have got these values. And here you know that Z equals to, for helium system, number of proton will be 2. So z equals to 2. So don't forget to put z equals to 2. So after we get this value, right? And there are some equations. Okay, so now now let's have a look in SI system. So the equation is similarly slightly changed. Okay, because this is, we have to include the 1545 epsilon naught value, so that I have shown in my last video. So see that and you will get this value, this radius equation. And now you have, if you put all these values in SI unit, okay, you will have this value, this fast Bohr radius, Bohr orbit. Okay, this is also called Bohr radius. Okay, so now let's calculate the velocity. So to calculate the velocity, we will have this equation that I have shown in my last video. So for n equals to 1, that means the first Bohr orbit, we will have to put all the values, all the equations, all the values of h, m, rn, that means r1 means r1 we will get from here. Okay, so the put r1 value, that means first Bohr orbit value, in the equation, okay, from the first equation from here. So now if you put this value, you will have this velocity over here, and finally if you, in case of SI system, you can calculate easily. Okay, so I am not making you bored, so that you can easily get that. Just pause the video and understand what I am telling you. Next, I want to calculate the energy of the electrons for helium plus systems. So to calculate the energy, the equation, you know, this for SI system and this for CS system. So let's calculate SI system for SI system first. And I have told you we are calculating the energy for helium plus systems. That means Z, number of proton, will be 2. So no, don't forget to put Z equals to 2. So take care of that value. Okay, these are hydrogen like systems, but the number of proton are different. Okay, for lithium 2 plus, the Z equals to 3, beryllium 3 plus, Z equals to 4. So don't forget that one. Okay, because many students do a lot of mistake over in that case. Okay, so now put all those values and you will have this amount of energy, in joule in SI unit. Similarly in CS unit, if you put all the values in CS unit, then you will get this arc amount of energy for fast electron or fast orbit. Okay, as these are one electron systems. So okay, let me pause the video and okay, 1 second. So now I have included a lot of equations and a lot of relations, because a lot of students are not familiar with this kind of relations, but these kind of relations are very, very important. Okay, so first relation is about 1 kilogaussr. So this is the amount of energy. So this amount of energy you won't see. Okay, you haven't seen this amount of energy, this unit, but this is present in inorganic chemistry. So it will be better if you know this, if you are familiar, if you become familiar with this unit. Okay, kilogaussr, this is the amount of energy. So 1 kilogaussr equals to 11.97 kilojoule per mole, and that is equals to 1000 centimeter inverse. So you can interconvert to anything. Then 1 kilojoule equals to 1000 joule, that is, you know, 1 electron volt, that is equals to 1.6 multiplied by 10 to the power minus 19 joule, and 1 joule equals to 10 to the power 7 arc. So these equations, that will help you a lot when you interconvert the energy units. Okay, so let's have another problem. Let's practice another problem. So the another problem is about the calculate the third ionization potential of lithium atom. So here it says the lithium atom, but focus on these 3 words. Third ionization potential, that means for lithium 2 plus. So lithium to lithium plus, first ionization energy, lithium plus to lithium 2 plus, second ionization energy, lithium 2 plus to something else, that is third ionization energy. That means this is one electron system, right? So this line means for lithium 2 plus systems, you have to calculate the ionization potential. That is called third ionization potential, right? So I have already shown you this, how these equations generally come. Okay, because you have to the work done you have to do to change the electron's position from a particular orbit to infinity. Okay, so the amount of work done you have to do, that is called ionization potential. So how this equation came, that I have shown you in the last video, so check that video. Okay, I'm just putting the value. So here for this you have to put this n1, and here it is infinity, because you have to send the electron to infinity number of orbits. So n equals to infinity, so infinity square will be infinity. And from where? From n1. So remember this equation, 1 by n1. So from where you are sending the electron, and from to where you are sending the electron. So to where, that would be infinity. So 1 by infinity, that would be 0. Okay, and 1 by n1, from where you are sending, that is the first orbit, of course, as this is a lithium 2 plus system. I have shown you, I have told you already the third ionization potential, that means that generally occurs for lithium 2 plus system. So for lithium 2 plus system, this is the one electron system, that means for fast orbit, N1 equals to 1. If you put 1 to 1 square means 1 by 1, that will be 1. So here you got the equation. So for lithium system, Z value equals to 3. Okay, and if you put all other values, you will have this equation in Joule unit. Okay, and from Joule, how to convert in electron volt, that I have shown you. From Joule and electron volt, the relation is this. So if you interconvert this these two units, then you will have from Joule to electron volt per ion. Why ion? Because this is the lithium 2 plus system. Okay, now if you convert these equations in other units, so you can do that. Okay, so Joule per ion, Joule per gram ion. Okay, so you have to include the Avogadro number like that, Joule per kilojoule gram ion. So you can do that, of course. Okay, so this is quite easy. Other things, mole concept like things. So I hope this problem is solved. Listen one thing, if you don't understand what is ionization potential, I will recommend you to watch last uploaded video, where I have shown you how from Bohr theory how ionization potential concept generally comes. Okay, so see that video, then you will definitely get that how this equation came. Okay, so another question, let's have a look at that. So here the wavelength of the first member of, that is first member means H alpha line of Balmer series of hydrogen atom is this. The wavelength is given. Calculate the wavelength for H beta line. H alpha line, so Lyman Balmer, that means second, n equals to 2. So let's have a look at that. So this is Balmer series, that means this one. Okay, this one. So alpha line means from transition from n equals to 3 to n equals to 2 is given, the wavelength is given. You have to calculate the wavelength for n equals to 4 to n equals to 2. Okay, so yeah, n equals to 3 to n equals to 2, that is given H alpha line, and n equals to 4 to n equals to 2, that is H beta line. Okay, so you have to get this amount of the wavelength for this transition. So what I did, what I did for alpha line, I have I have written the equation. Okay, and as this is a hydrogen atom, so here Z square should be multiplied, but Z equals to 1 for hydrogen atom. Okay, so that's why Z square equals to 1. I did not include Z square. Okay, as Z equals to 1 over here. So for alpha line 3 to 2 transition, for beta line 4 to 2 transition. So we have got two different equations, and we know about the R Rydberg constant. So this is a constant. So if you can generally do subtraction, so you will get for nu bar alpha equals to this and nu bar beta equals to this. Okay, and R will be R. Then if you divide this in such a way so that nu bar alpha divided by nu bar beta, then you will have this value. R will cut because this is a constant, Rydberg constant. Then nu bar beta, that is normal calculation I have done. So I have taken the nu bar alpha to that side. Okay, and finally I have put the nu bar means what you know, this is called wave number, that means 1 by lambda, that is 1 by wavelength. So I know the wavelength for alpha transition. Okay, H alpha transition, that means nu bar equals to 1 by lambda. So in the place of nu bar alpha I have put 1 by lambda. So lambda means this value. Okay, so I have put that one over here. So then this is the equation of nu bar beta. So nu bar beta means 1 by lambda beta. Okay, that is equal to this, and I have just calculated the lambda beta value from this equation. So I hope this problem is also very, very clear to you. Okay, so just understand what is alpha line, what is beta line. So if you understand those, then it is quite easy how to solve these kind of questions, that you can easily solve this kind of questions. Okay, so this is a homework. Okay, so you can do it in your home. So just to solve it and comment below, that then I will verify you. Okay, I will tell you whether this is the right answer or not. So just read the answer. I have provided you the answer key. Okay, and just to practice this problem. Okay, so just check and tell me that whether you are getting this answer or not in the comment box. Okay, so this is a problem, just solve it yourself. I hope you can do that if you understood this kinds of problem. Okay, now I am coming to Sommerfeld atomic model. So why Sommerfeld atomic model came? This is the first question. So what happened? In generally, what happens? Bohr told that from n equals to 2, n equals to 1, this kind of transition can be possible. But in experimentally, what we are seeing that from n equals to 2, n equals to 1, according to Bohr, from n equals to 2 to n equals to 1, that is one transition is possible. So we can get one line spectra, one single spectral line, okay, like this. Okay, you can see. But actually, we are not getting only one line. Experimentally, we are getting a lot of lines. These are called fine spectrum. So that means this one line has this amount of lines, this number of lines present in this, but we cannot see these lines. Bohr theory generally is on the fact that transition from n equals to 2 to n equals to 1 generally occurs. But Bohr couldn't explain the fine spectrum. That means how we get this amount of line, this numbers of line. So just take a logic, okay, and think when we get a lot of lines over here. So if transition generally occurs from n equals to 2 to n equals to 1, we definitely get one line, because one transition, one line. But from if transition generally occurs from n equals to 2 to n equals to 1, we are getting a lot of lines. Why is that? That means here in this n equals to 2, a lot of other energy levels are present. That means n equals to 2 includes a lot of other energy levels, and n equals to 1 includes a lot of other energy levels. So these other energy levels are participating in these transitions. That's why when transition occurs from n equals to 2 to n equals to 1, we are getting a lot of lines, because n equals to 2 include a lot of line, okay, a lot of energy level, because this is energy level, this is another energy level, okay, and these energy levels are quantized. That means electron cannot stay in between these two energy levels. I have discussed this in Bohr theory, right? So here n equals to 2 will include other lines. So how it occurs? Okay, I am giving you a hint that I just read this point, but I am giving you a hint that, like, if you have listened already about azimuthal quantum number, okay, magnetic quantum number, okay. So this is how these lines came. So n equals to 2 include other lines also. So how those are coming, I will discuss in the lateral section, or just keep watching this video. So I hope I can make you understand this fact that how we are getting a lot of lines, because n equals to have other energy, a lot of n equals to 2 will have a lot of energy levels, and n equals to 1 will have a lot of energy levels, and those energy levels are participating in transition. That means suppose n equals to 2 have 7 lines or 5 lines, for example, 1 2 3 4 5. So 1 to here, or other lines are present, so 1 to here, 2 to here, 2 to this, 2, like that transition as is occurring. Okay, so that is why we are getting fine spectrum, fine structure. So this is how Sommerfeld started to discuss his atomic model theory. Okay, so how we are getting that? So according to Sommerfeld, electrons are revolving around the nucleus in some specified elliptical paths. So what Bohr told us? Bohr told us that electrons are revolving around the nucleus only in circular orbits, here like this. But Sommerfeld told us that no, not only circular orbits, electrons are revolving around the nucleus in elliptical pathways, elliptical orbits, right, like this, in this way. And in these elliptical orbits, when you know that this is called semi-major axis, and this is called semi-minor axis. I have not drawn that one. So semi-major axis, this one, and semi-minor axis, this one. So when semi-major axis and semi-minor axis becomes equal, that would be a circle. That means Bohr atomic model is a special case of Sommerfeld atomic model. That means Sommerfeld atomic model can explain also the Bohr atomic model. Okay, so when semi-major axis and semi-minor axis gets equal, then that will become a circle. Okay, otherwise it will be an ellipse. Okay, and what happened in case of Bohr atomic model, we will have only one variable, okay, that can explain the position of the electron, that is the distance from the nucleus. Okay, so because angle or distance, okay, any one of these, because all time the distance is constant. So if you get the radial angle from here to the electron, you will have that, yeah, the position of the electron is here. But in case of Sommerfeld atomic model, as this is an ellipse, so you will have the distance, that is r, and this angle phi. Okay, so these two variables are important in case of Sommerfeld atomic model, right? So now, so at any instant position is r comma phi. So we are needing these two variables to locate the electron, and the allowed elliptical orbits will follow these two conditions. So these two conditions, these are quantum mechanical. These came from quantum mechanical calculations. So don't think that how these are coming. Just understand that what are these. So p phi d phi equals to kh, and pr dr equals to nrh. So what is p phi? P phi is the angular momentum of the electron based on this angle phi. Pr is the angular momentum, radial momentum of the electron based on this distance r. Okay, so this is p phi d phi, and d phi, you know, the integral small differentiation value. Okay, that is required to do the integral. And why I am using this cyclic integral? Because this is revolving around like a cycle. Okay, it will come here again after one revolve. Okay, that's why I am using here cyclic integral. So that will be kh and that will be nrh. So what is k? K is called azimuthal quantum number. So now, when Sommerfeld is discussing his atomic model, he has told that yeah, n would be one quantum number. That means a variable that we will call quantum number the principal quantum number, and k that is defined as azimuthal quantum number. But initially k is called azimuthal quantum number, but later on you will see that k will be replaced by L, which we will call as azimuthal quantum number. But I will come to that later on. And we know that nr, that means radial quantum number. Nr, that is radial quantum number. Remember, n is principal quantum number, but nr will be radial quantum number. Okay, so we have to have one quantum restriction over here. Okay, so here what happens, nr and k, how these are related to each other. N, that is principal quantum number, will be equals to radial quantum number and azimuthal quantum number. That means, try to remember, this is a principal quantum number, that is n equals to 2, and that will have two other level, one azimuthal quantum number, one radial quantum number. Okay, are you getting that? So this can be divided into other energetic parts, but this is not exact explanation. I will go into very deep section, but just try to imagine what I am telling about. This n will have two other energy levels. Okay, nr and k, like this. Understand, like this way. Okay. So, and I have told you that Bohr atomic model has one quantum restriction, and Sommerfeld atomic model has two quantum restrictions. Okay, and which are those I have already shown you. And another thing I want to add over here is that this atomic model is very successful, okay, than Bohr atomic model, right? So let's go forward. So now, but these atomic model will have some kind of limitations, and what are those limitations? We will see those limitations once we solve those limitations. Okay, so let's do fast modification of that limitation. The first modification, as I have shown you that this will be the semi-major axis and this will be the semi-minor axis. This is called A, this is called B, right? And here it is the nucleus, and here it is the electron. So electrons are revolving like that. That means the distance from the nucleus of the electron is increasing. Sometimes it is increasing, sometimes it is decreasing. That means sometimes it is highest and sometimes it is lowest. Okay, so this is called the maximum distance. When this is the maximum distance, then it will be called like perihelion, or when it is the minimum distance, it will be called like aphelion. Okay, so this is you know, from your solar system like things. Okay, so now this semi-major axis and this semi-minor axis, right? So if this is A, how this semi-major axis and semi-minor axis is related to these quantum numbers? Okay, so you can see that AN is related to like this, BN is related to like this, where A0, you know, A0 is the Bohr fast orbit. Okay, the R0 fast Bohr orbit. So this is a constant, 0.53 Armstrong its value has. So why I am putting N over here? An means fast second, like that. Okay, so that can be for fast elliptical orbit, that can be second elliptical orbit. So for fast N equals to 1, for second N equals to 2, like that. That's why I am taking N values. Okay, so that I can put N value over here also. So now if I divide like this, Bn divided by An, what we get? Everything will cut and we will get K divided by N. And if we put the value of N, that is Nr plus K, we will have K divided by k plus nr. And remember this an, that is semi-major axis, this value is governed by principal quantum number n. How? Please see, this an has only variable n, these are constant, but bn has two variables n and k, that is principal quantum number and azimuthal quantum number. That means the semi-major axis is governed by only one quantum number, that is principal quantum number, but semi-minor axis will be governed by two other quantum numbers, that is principal quantum numbers and azimuthal quantum numbers. So remember these two one. So we know that n equals to nr plus k. That means how these are related to each other I have already shown you. But what will be the values of, because we know the values of n 1 2 3 like that, but what are the values of k and nr, how these are related to each other? So for a particular value of n, that means that would be n, k value will be 1 2 3 4 dot 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 n, that has a lot of possibilities. Nr value will have, when k equals to 1, nr will be n minus 1. So that for a particular value of n, if we add these two, we will get the value of n. That means if you add 1 and n minus 1, that will be 1 1 will cut and you will get n. But this will, if you add this, you will get n. This will, if you add this, you will get n. If you will add this, you will get n, and finally you will get n also over here. So if you put n equals to 2, then that will be 1 and this will be 2 minus 1, so that it is 1 plus 1, that will be 2. Okay, so this is how it works. But here there is a problem. Okay, the problem is, you can ask that why I have started the value of k from 1, why not from 0? Okay, I have started this from 1 and I know that nr plus k should be equals to n, so I can start from 0 and that is n, so 0 plus n, that will be n. So I haven't started that, I have started from n equals to 1. Why? So let's solve this problem in a mathematical way. So if you put k equals to 0, that means over here k equals to 0, then it will be b equals to 0, bn equals to 0, like this. Okay, from this equation. And if bn equals to 0, that means this line will not be present. Okay, the length will be 0. That means electron, nucleus, atoms, everything, that means atom will be linear. So electron and nucleus will be linear. That means sometimes electron will cross the nucleus and sometimes it will be in a linear way. So linear atom, this is quite wired. Okay, so linear atom is not possible. That's why k equals to 0 isn't possible. So I have started the value, I am starting to take the value from k equals to 1 to n, right? But finally we will change the k value from k to l, we will call azimuthal quantum number based on Schrodinger wave equation theory, advanced quantum theory. But now I will keep it k. Okay, so now you know that this equation is present, and you know that another thing is, if you put here, you can see that an is not dependent upon k. Okay, a is not dependent upon k. So here this one, bn by n equals to k by k plus nr. So if nr, that means radial quantum number, is 0, then k divided by k, that will be 1. That means bn will be equal to an. Bn will be equal to an. That means this line and this line will be equal, and when it is equal, so it will be a circle. So that's why I told you that Bohr atomic model is a special case of Sommerfeld atomic model. That means Sommerfeld atomic model is capable to explain the Bohr atomic model, right? So this is quite amazing, right? So now this is when nr becomes 0, that means radial quantum number becomes 0, the elliptic orbit becomes circular orbit, Bohr circular orbit, right? So that's why I told you that Bohr circular orbit is only a special case of Sommerfeld's model. Okay, again, just look at this first part. Okay, don't look at this part. Okay, so if you look at this part, you will have that when k will be equals to n, that is k equals to n. Okay, because k can never be greater than n. Okay, maximum it can be k will be equals to n. This is how. Okay, k value maximum will be n and nr value will be 0, then nr will be 0 and k will be n, so n equals to n. So when k is equals to n, that means the maximum value of k, then Bn will then this two part will be cut and here one will come. That means Bn will be equal to An. So when k equals to n, for the maximum value of k, Bn will be equals to An. That means Bohr circular orbit. So in generally what happens, when the value of k increases, the ellipticity of the orbit decreases, and for the highest value of k, that means the k when k equals to n, it becomes circular orbit, and for minimum value of k, it is the most elliptic in nature. That means like this system, and when it k is equal to n, it will be like that, circular orbit. Okay, so I think it is quite clear to you. So now I have discussed about the orbit. Okay, so I should keep there the orbital. Okay, so I mistakenly have write here, I have written here orbit. Okay, so please make this right, that will be orbital. So now when k equals to 1, don't look at this part. Okay, don't look at the L part. I'm making you understand this part later on. Look at the k part. So when k equals to 1, S will be the orbital name will be S. When k equals to 2, this will be P. When k equals to 3, this will be D. When k equal to 4, this will be F, and so on. So how do I elaborate these things from this theory? Okay, let's elaborate this one first. So look at these pictures. So for 1s orbital, that is, so these are nothing but the nomenclature. Okay, so don't think that these are anything. There are some meaning of S, P, D. F, S means sharp, P for P for principal, D for diffuse, F for fundamental. So these are terms coming from those parts, and these generally came from spectroscopic phenomena. So when the spectra is sharp, so S is S. When this is principal, like P, diffuse like D, and F for fundamental like that. Okay, so these generally are term. Okay, so don't go into deep for this. Just understand these pictures. Listen, for 1s orbital, that is 1s means ns, that means n equals to 1 over here. So if n equals to 1, k value, I have shown you that k value starts from 1. So k will be equal to 1 and nr will be equal to 0. So n equals to 1, k will be 1, so nr will be 0. So n equals to k. So when n equals to k, that means n equals to k, an will be equals to bn, that means Bohr circular orbit. That is why we draw the 1s orbital like a circle. Okay, when k equals to 1 and n equals to 1, that means when k and n equals to 1, k is equal to n, the orbit will be circular, or orbital will be circular. Okay, just understand in this way. When this is, of course, this is not advanced quantum mechanics. Okay, this is the old quantum theory. Okay, because orbitals are not looking like this. Okay, the actual orbital are different. Just understand in the concept of Sommerfeld atomic model. Okay, so in the second case, if you consider 2p orbital, that means n equals to 2, p equals to what? P equals to, for according to k, p equals to 2, n equals to 2, k equals to 2. So when n equals to 2 and k equals to 2, that will be circular. When because k has two possibilities over here, because k value will start from 1. So if n equals to 2, k will have values 1 and 2. Okay, so if k values 1 and 2, that means there is some radial, okay, radial part will be present. That means the radial angle will be present. If angle will be present, so that will be a elliptical orbit. So that's why here this is an elliptical orbit. So n equals to 2, k equals to 2. Circular orbit, n equals to 2, k equals to 1. This will be an elliptical orbit. So as k value is less than n value. Similarly, if you take 3D orbital, so when n equals to 3 and k equals to the circular orbit, and then when k value decreases, the elliptic properties, elliptic character will increase. So here k equals to 2, n equals to 3 will be like this. K equals to 1, less value of k, or more elliptical nature. Okay, so this is how it works. So now the question that I can solve, that from these concepts, how can I explain the fine spectrums? Okay, because we are doing the fast modification from this theory. Okay, then the modifications are like this. Okay, so k value, nr value, and we are putting different k values and nr values. And from these modifications, how can I explain the fine spectrum from Sommerfeld atomic model? So this is very important. How can I explain that one? So let's have a look at that. So how to understand those? So let's have a look at for Balmer, first Balmer series, that is alpha Balmer line, that is transition from n equals to 3 to n equals to 2. Okay, so I know this formula. I also know these possibilities, because when n equals to 3, k value will be 1, 2, 3, that is starting from 1, and for n equals to 2, k value will be 1 and 2, and these two nr value and k, that after summation we will get n value. So when k equals to 1, nr will be 2, k equals to 2, nr will be 1, k equals to 3, nr will be 0. Similarly, this is true. So that means I have told you in over here that this energy level contains a lot of other energy levels, and even this energy level includes a lot of other energy levels. That's why transition occurs from different energy levels, and we are getting different lines. Those are explained by the Sommerfeld's fine spectrum model. Okay, so n equals to 3, that is n, this is 3, n equals to 3, and this is n equals to 2 level. So n equals to 3 level contains 3 different lines, and n equals to 2 levels contains 2 line. So this you can show that is one line, but actually in quantum level this is not only one line. This is actually a lot of lines. This has a lot of energy levels, and this also has a lot of energy levels. This is 3 energy levels, this is 2 energy levels, right? So yeah, so now 2 energy levels, 3 energy levels. So this is n equals to 3 and this is n equals to 2. So transition occurs, so there are a lot of possibilities that transition can occur. So you can see a lot of possibilities, but actually the linear line, not the dotted line, these lines are actually accepted, other lines will not be accepted. Okay, so I will discuss this later on, but these are the possible spectrum lines that we can get from the first modification of Sommerfeld atomic model. So you can you are understanding that Sommerfeld model more or less can explain the fine spectrum, but especially it is good. It can explain the fine spectrum at least. Bohr theory was completely unable to explain the fine spectrum. Okay, so this is how it works. Now I want to do Sommerfeld's second modification. So what is that? Okay, so I want to talk something before I discuss this one. Okay, so what happens when Sommerfeld's second modification was done? So you know that when this is the nucleus, this is the electron. So the largest distance, when the electron is in maximum distance, so it will we will say that this is in the perihelion position, and when the distance is minimum, we will say that it is in the aphelion position. So that means this is nucleus positively charged, this is electron negatively charged. So electrostatic attraction works between them. So when the electron is in perihelion position, that is in the maximum distance, then the attraction force will be lowest. When it is in the aphelion position, that is in the minimum distance, at the minimum distance, the attraction force will be higher. So as these attraction force are changing continuously, because the distance are continuously changing during revolution of the electron, so energy of the electron, energy of the system is changing, and this energy we can explain with this equation. Okay, you can see the equation, and in this equation you will see that in this energy expression n and k both terms are present. That means energy of any particular level, that is for n equals to 1, n equals to 2, different E1, E2, energy of a particular energy level doesn't only depend upon n value, it also depends upon the k value, because k and n both terms are present in the energy expression. Okay, so now come back to this point. So this is energy level 3, this is energy level 2. So these energy levels are based upon n and k values. That means energy levels are both n and k dependent. That's why you are getting a lot of fine spectrum, a lot of transitions, and hence a lot of fine spectrum. Okay, so the total energy of the electrons depends upon both k and n value for a particular value of n. Okay, and this is what the distance is changing continuously. Okay, so this is what I have shown in this picture, nothing else. So, but the problem is, I have told you that all the transitions are not possible. So actually, if here 6 possible transitions are possible, okay, 6 possible transitions may occur, but experimentally we can see that Balmer series, that means n equals to 3 to n equals to 2, Balmer series will have 3 spectral fine spectrum. That means from Bohr atomic model we are getting 1, but actually the number of fine spectrum is 3 for the Balmer series. But here from these we are getting 6 spectral lines. Okay, include all the linear plot or dotted plot. Okay, include all this. So 1, 2, 3, 4, 5, 6. So we are having 6 spectral lines. So these 6 spectral lines, so actually experimentally we are getting 3, but it explains the 6 lines. So here to explain this fact, another term is included, that is selection rule. So see, what is selection rule? You are familiar with this term. Selection rule means a rule that select that this will be the rule that should need to be followed to make the transition. So during transition, the selection rule should be delta k value will be plus minus 1. So the difference between two k level, k energy level should be plus or minus 1. That means n value are 3, n value 2. So according to if you only consider n value, then all transitions are possible. But only these transitions are possible if you consider the k values. If you consider these lines, take this line, then n equals to k equals to 2, and this k equals to 2. 2 minus 2, that is 0. Not possible because it violates the selection rule. So selection rule is important. So this is the selection rule that explains this transitions phenomena, and delta n may be any values. Okay, so from different lines, alpha, beta, gamma lines we will get. So delta n may be any value, but delta k should be plus minus 1. This is one important quantum restriction that we call selection rule to explain this fact. So that is why we are getting 3 lines for Balmer series. So we will tell alpha Balmer line, that is n equals to 3 to n equals to 2, is we will have 3 different lines, 3 fine lines or triplet. Okay, I hope this is totally clear. Now I have told you that I should apply the concepts of Sommerfeld atomic model, and I will explain the penetrating power of orbits, or the shielding power, or the screening power. You know all these terms, you are familiar with because you have already read these terms in your first year examinations in periodic table chapter. So what is penetrating power and how this penetrating power came into consideration? Okay, so let's have a look at that. How this came from Sommerfeld atomic model. So let's have a look at that. So you are familiar with the term of ellipticity. So how much it is elliptic? Okay. So if ellipticity increases, the attraction force of the electrons towards the nucleus increases. Okay. And also if ellipticity increases, the shielding power or screening power of the nucleus, of the orbits, that means the electrons present in that orbit, also increasing. So ellipticity is proportional to attraction force between nucleus and electron, and which is proportional to shielding or screening power, that is penetrating power. So what happens when the ellipticity increases? The inner orbit, the orbit which has more elliptic, those orbit becomes inner orbit. That means those orbit makes a layer around the nucleus. If those orbit makes a layer, so in those orbits electrons are present. So positive around the positive charge, a negative charge layer is present. So attraction will not go outside that layer, outside that electron layer, outside that orbit layer. Okay. So if this thing occurs, then those orbit becomes inner orbit, which orbit makes the layer. And if those orbit becomes inner orbit, it will prevent the outer orbits from facing the nuclear charge. So if we make an order of sp-df orbitals or sp-df electrons, s orbital will have most of course ellipticity. Okay, then p orbital will have lower ellipticity, then d orbital, then f orbital. So ellipticity decreases in such a way, and also that's why as ellipticity is proportional to shielding or screening power, so penetrating power, so penetrating power will decrease along sp-df electrons. So this is how this penetrating power comes into consideration. So this is important, and this is very fundamental. Okay, so now let's have a look another thing like merits. So what are the merits and demerits of Sommerfeld model? So we have totally understand what is Sommerfeld model, different spectral phenomena that Sommerfeld model can explain. Okay, but there are a lot of demerits also. So the merit is Sommerfeld model can explain the fine spectra. Okay, that I have shown you. Sommerfeld model can explain the penetrating power, And also Sommerfeld model can explain a lot of other things like quantum defect. So it is not in the syllabus, this is advanced thing, so I am not getting into that. Also Sommerfeld model can't explain a lot of components present in fine spectrum. Okay, because Sommerfeld model generally takes this delta k equals to plus minus 1 value, this quantum restriction, because it need to follow, it need to verify, it need to follow the experimental results. Okay, this is why it is taken. But how this is coming, okay, Sommerfeld did not explain that one. So in the fine spectrum, Sommerfeld model did not explain the other components of fine spectrum. Then Sommerfeld model has azimuthal quantum number, okay, so that is k, but actual azimuthal quantum number is is L. So let's see what is that. So to understand that, I have to go to this slide. That is, actually we are from Sommerfeld model we are getting azimuthal quantum number k, that is value 1, 2, 3, 4 like that. But from wave mechanics, Schrodinger wave mechanics, that is modern quantum theory, so that is much more correct. We are getting the exact azimuthal quantum number, that is L, and k and L are related like this, L equals to k minus 1. So for s orbital, L value will be 0, for p orbital, L value will be 1, 2 and 3 and so on. So for your exam, you have to remember the L value, not the k value. Okay, this was the old rule, okay, old concept. But in that case, Sommerfeld, to explain the Sommerfeld model, you will need k. But actually azimuthal quantum number is L, and those are related like this. Okay, so then according to Sommerfeld atomic model, it doesn't follow the Heisenberg uncertainty principle. That is because you can explain, you can locate the electron, you can locate the electron's position and momentum at a particular time. Okay, that means it is following some kind of classical mechanics, as it is included some kind of classical mechanics, and it is also included some kind of quantization of energy fact. That's why it is also following the old quantum theory, or it follows the old quantum theory, or it is the part of old quantum theory. Okay, so these are the demerits. A lot of other demerits are also present. So these are also the demerits. So another demerits, maybe you can tell, that was present also for Bohr theory, that is, it is not applicable for polyelectronic system or multi-electronic system. Okay, so these are the demerits. So I hope total Sommerfeld model is completed right now, and if you understand these things, if you have any problem, you can comment below. And if you are preparing, but I am making this video especially for IIT exam examination, but this will be very helpful for other advanced examination, because I am going into deep. Okay, if boys has some problems, so I am sorry for that, because in hostel some kind of problem I have to face, but I think that is quite okay. But if you are preparing for this exam, especially this exam, so I am providing a lot of things. Okay, so if you can self study, okay, and if you can easily crack the examination, I will after getting all this preparation kit, okay, I will add you in my WhatsApp group. Over there you can solve any problem with other students, with your friends. Okay, I or any of the WhatsApp members will solve the problem, and you will also get the free practice sets. So this all you will get. So whatever, let's finish this video. See you in next video. Thank you. Thanks for watching.